Okay. All right, welcome everybody. Sorry for the technical difficulties this morning. We'll go ahead and get started here. So first we're going to look at how many H&MR signals are going to be in each of these molecules, and then we're going to draw a rough H&MR graph. Okay, and feel free to ask any questions via your mic or in the chat. Okay, so first we want to look at how many signals are going to be in the following molecules. And the first step is to determine if there's a stereocenter in the molecule. If there is, all of the CH2s will be different signals from each other. Okay, so that's the first thing you need to look at to determine how many signals will show up on a graph. Are there any stereocenters in this molecule? No, right? Perfect. Nice job, Tanner. Okay, so all the CH2s will just be one signal. Okay, so let's start here on the right side. This proton will be our first signal. We'll call this HA. And again, I'm drawing with my finger, so I apologize. And then these hydrogens over here, these will be our HBs, HC, and HDs. Okay, so those are all of our signals for this molecule. Okay, so now we're going to draw a rough H&MR graph. And you want to determine which one's going to be furthest downfield. So basically the ones that are furthest downfield are the ones that are closest to electronegative atoms. Okay, so which one's going to be furthest downfield, do we think? HA, perfect. Okay, so HA is going to be our furthest downfield. All right. But we want to determine how many peaks are going to be there with HA. Okay, so how many neighbors does HA have? To determine neighbors, you have to have a hydrogen within 3 sigma bonds. So that's perfect. Tanner says there's 0. There are no hydrogens within 3 sigma bonds, so 0 neighbors. And we use the N+1 rule, which makes this be 1 peak. This is our HA peak. Okay, 1 peak means there's no neighbors. Now, what's going to be our next most deshielded? HB, perfect. Okay, now we need to determine how many neighbors it has. And there are hydrogens within 3 sigma bonds here. So HB has 2 neighbors, and they're the HC hydrogens. Okay, if you want me to show that, let me just show this on this first one. Okay, so there's 2 hydrogens here, 2 hydrogens here. So if you look at the number of sigma bonds from this hydrogens all the way to here, that's 3 bonds. Okay, we go from hydrogen to carbon, carbon to carbon, carbon to hydrogen. Okay, 3 sigma bonds. Okay, so that means that they are neighbors. Okay, so these are HBs, HCs. So HB has 2 neighbors, which are both the HCs. We use our N+1 rule, gives us 3 peaks. Okay, there's our HB peak. How many neighbors does HC have?
One neighbor.
Okay, I heard 1 and we got a 5 in the chat. Okay, so there's 3 hydrogens on the end here, and those are within 3 sigma bonds, and then HBs are also neighbors to HCs, so there's a total of 5. Nice job, Tanner. Okay, and so looking at this, you have to determine, I know it's getting a bit crazy in here, and I'm sorry I have to draw with my finger, but okay, so you've got these 3 hydrogens and these hydrogens. Okay, so the HCs, okay, they have these neighbors, 1, 2, 3. So all 3 of those, and 1, 2, 3, those 2. So that's a total of 5. Does that make sense to everybody? Did I explain that well enough? Anybody still confused? Cool. So 5 neighbors, N+1 rule means there's 6 peaks. So we have 1, 2, 3, 4, 5, 6. Those are HC. And then lastly, we know that HD has two neighbors because HC was their neighbor. Okay, so there's two neighbors for HD, which means 3 peaks. Okay, does that make sense to everybody? Any questions? Awesome. Okay, so for the rest of these, I probably won't draw the HNMR graph just because it's not very pretty with my finger, but I will send you guys the key afterwards so you can see it and see exactly what I would do. But the rest of them, they're not so picky as far as like the order goes, how de-shielded they go. I was more concerned about some of the patterns that we're gonna see. Okay, so I'll talk about some of those patterns. All right, so this tert-butyl group, all 9 of those hydrogens at the end of the carbons, they're all in the same field or same, they're the same type of hydrogen. Okay, so those are all HAs. Okay, then there's no stereocenter here, so these are HBs, HC, HDs, and HEs. Okay. And what you want to look for in an HNMR graph is if you see a single peak that's very tall and the, I'm trying to think of the name of it right now. What's the integral value? The integral value, you guys remember the integral values? Okay, if the integral value tells you there's 9 hydrogens and there's only 1 peak, you know that it's a tert-butyl. Just some little tricks to look out for. Wow, this is very difficult with my finger. Okay, tert-butyl group. So if you see one large peak with 9 hydrogens, the integral value tells you there's 9 hydrogens and there's 1 peak, you know it's a tert-butyl group. Okay. All right. Now let's go down to this next one. We've got these two are the same. Okay, so those are going to be HA. This hydrogen here will be HB. HC and HD. Okay, so 4 peaks on this one. Okay, and the kind of the pattern you're going to see here is if you see a multiplet, okay, which is like a bunch of peaks basically, and it has 2 hydrogens, and then you also see, sorry, you see a multiplet with 1 hydrogen. And then you see a doublet with 6 hydrogens. Okay. That's going to tell you that you have an isopropyl. Okay. So 1 hydrogen that's a multiplet and 6 hydrogens with 2 peaks, then you know you have an isopropyl group. Okay. So just look out for some of those patterns there. Okay. All right, let's carry on to this next one. Let's skip this one for now just because it's going to be hard to draw, but you guys can look at the key for that one. Okay. Now rings are a little bit different. Sorry, we had a question here. Is the tert-butyl supposed to be HA on the second one? Let's see. Yeah, that would be HA. Yep. Sorry, it looks like a D. It's really hard to draw with my finger. HA. Does that look better? Yep, you got it. Okay. So with rings, you just got to be very careful with your hydrogens here, which ones are the same and which ones are different. We're going to ignore the graph on this one. I just wanted to talk about how you determine which ones are which, okay? So I'm going to color code each of these, okay? So the chlorine is on the front carbon, okay? And these two hydrogens are going to be identical, okay? Because they're in the same proximity to the chlorine, okay? Now we're going to look at the next type of hydrogen, the one attached to the chlorine. Okay, there's no other hydrogen like that one. That one is very unique because it's so close to the chlorine. And then the last two here are both the same as well because both of them are facing away from the chlorine and equally far away from the chlorine. Okay, so those are the same hydrogens. Okay, so I just wanted to talk about the differences there. All right. And then we're going to ignore the graph on this one as well. But I wanted to show you guys the different peaks here, okay? So first of all, we have our HAs, okay? We have a hydrogen here, this will be our HB, okay? And because we have a stereocenter, all of these four different hydrogens are all gonna be different from each other. So we're gonna have HC, HD, HE, HF, and then these three on the end, HG. Does that make sense to everybody? How when there's a stereocenter in the molecule, which is right here, okay, that's our stereocenter, then our HCH2s are going to be separate signals from each other. Okay. Any questions on that? Okay. So we're going to determine the number of protons in the following H&MR graph. I wonder if I can insert a table. No, I'll just draw it. Okay. So this is what I was talking about with the integral values. Okay. So this is going to tell us how many hydrogens are represented by each of the peaks. Okay. So what you want to do is take the integral value, which is 27 for this first one, and divide it by the lowest number of all of the integral values, okay? Which in this case is the 27, okay? And we're going to do the same thing for all of them. So let me start over here. 27 divided by 27. 40.2 divided by 27. 28.4 divided by 27, and 42.2 divided by 27, okay? And when you do that, this one equals 1. The second one is about 2. The third one is about 1. And the last one is about 2, okay? Now, these numbers do not have to be exact. They don't even have to be super close, okay? Like something, if you divided 40.2 divided by 27 and it was 2.4, that would count as 2, okay? So you just have to be in the general region. If it's closer to the bigger number, round up. If it's closer to the smaller number, round down, okay? Just get close enough, okay? And if these didn't end up being whole numbers, right? If it ended up being exactly 2.5, okay, then you'd want to multiply all of these by 2 in order to get all whole numbers. Okay, but all of these came out good. We'll have an example that looks like that in just a minute, okay? So we know that this peak has one hydrogen, okay? So that's one hydrogen with two neighbors because there's 3 peaks, okay? Then we've got this peak has 2 hydrogens, or yeah, 2 hydrogens, but there's only 1 peak, so 2 hydrogens with no neighbors. This one is represented by 1 hydrogen, and that's 1, 2, 3, 4, 5, 6. Looks like 6 peaks. Okay, so it's going to have 5 neighbors. All right, and this last one has 2 hydrogens, and there's 2 neighbors there as well. Okay. So that's what the integration values tell you. It tells you how many hydrogens are in each of these peaks. This is not always an absolute number. Sometimes it's a ratio. Okay, sometimes this will be like 4 to 8 to 4 to 8, right? Whereas you know that, okay, it's probably not that many hydrogens in each of these peaks, but it's probably that's the ratio, a 1 to 2 to 1 to 2 ratio. Okay, and we'll see more examples of that coming up. All right. So now we're going to do the same thing. Okay. But this time we know the chemical formula, so we can know the exact numbers. Okay. So we have 54 divided by 23. We have 23 divided by 23. We have 33 divided by 23. So here, this one comes out to about 2.5. This one's 1, and this one's about 1.5. Okay. And so in this case, we want to multiply all of these by 2, and then we can check how many hydrogens we have. So if we multiply all of these by 2, we get 5 here, 2, and 3. Okay. When you add a 5 plus 2 plus 3, you get 10. And we know our chemical formula is H10. So we know these are the absolute values of hydrogens by each of these peaks. So this one is represented by 5 hydrogens, 2, and 3. Any questions on how I got that? Okay. Moving on to this next section, we've got, where if I can add, table, where did that go? Oh, okay, that's right. So, determine the multiplicity of each signal in the following molecules. So what we're going to want to do is, one, determine where the signals will be, and then write out how many neighbors they have. And so we'll say, you know, if it's going to show up as a singlet or if it'll show up as a triplet, okay? So, start on the right side here. Okay. So all these tert-butyls, right? These will be our HAs. How many neighbors does this tert-butyl have? 0, right? Okay, again, that is very, that's very important to remember with tert-butyls. There's not going to be any neighbors, okay? So what will this show up as? Will it show up as a doublet, as a singlet, triplet? What do we think? Singlet, right? Because there's no neighbors. Singlet. Okay, perfect. Our HBs here, what are they going to show up as? How many neighbors? What's it going to show up as? Perfect. So it's going to be a triplet because HB has 2 neighbors, which are the HCs. So 2 neighbors, you do the n plus 1 gives you a triplet. Okay. How many neighbors does the HC have? Just 2, right? Okay. So it's also going to be a triplet. Okay. Then we've got this hydrogen here, which is HD and HEs. Okay. All right. So HD, however horrible that looks, how many neighbors does HD have? 6 neighbors, perfect. All of the HEs, okay? So with six neighbors, how many peaks is that going to be? Does anyone remember what 7 is? Yep, it is a multiplet. There's a specific name that I'm not 100% sure if you want to know, but I would get used to it, is septet. Septet. Okay. 6 is sextet, 7 is septet, 8 is octet, 9 is nonet, and 10 is dectet. Okay. So just kind of know they're the normal, numbers as you go through 10. Okay. But anything over a 7 anything 7 and above is considered a multiplet.
Can you just show real quick the 6 on the screen?
Yeah, the 6 neighbors.
Yeah. I just want to make sure I'm getting it right.
Yep. They're these 6 hydrogens right here.
Okay, thank you.
Yep. Okay, and then HE has how many neighbors? Just one, right? On the HDs, so it's going to be a doublet. Okay. Let's do this next one. And again, it's very clear on the key. I apologize, I'm having to draw with my finger, but we're making the most of it. All right, so we have HA here. How many neighbors does it have? 0, right? No neighbors, nothing within 3 sigma bonds, so this is going to be a singlet. Okay. Now, we need to look, this is a CH2, okay? We need to look at if there's a stereocenter in this molecule. Is there a stereocenter? Yes, there is, right? Okay, so we're going to have HB and HC. What do you think HB is going to show up as? Okay, kind of a tricky one. It is a triplet, okay? Because you have HC is HB's neighbor, and you also have HD, which is this hidden hydrogen that's within 3 sigma bonds as well. Okay, so HB and HD, right? So that's going to be a triplet. Okay, HC is going to be identical, okay, because triplet, okay, because HB is its neighbor now and also HD. Okay. Now, how about HD? How many neighbors does HD have? Five, right? Okay, so it's got HB, HC, it's got HE, HF, and then HG is actually not a neighbor. Although it's within 3 sigma bonds, you can't go through an oxygen in order to count that as a neighbor. You can't move through an oxygen to be a neighbor. Okay, so that's kind of a trick you guys need to remember as well. You can't go through an oxygen in order to be a neighbor. So 4 neighbors. Yep, exactly. So HD, I know it's getting kind of confusing in here. HD will have 4 neighbors, which gives us 5 peaks, which is called a quintet. Okay. All right. Now let's do HE. How many neighbors do we think? We've got HF, obviously, HD, and all of the HIs. So 3, 4, 5 neighbors gives us a sextet. Okay. And the same with HF. And then HG, again, with the trick of not being able to go through an oxygen, that one, although it is within 3 sigma bonds of HD, does not count as a neighbor because you can't move through an oxygen. Okay, so that's going to be a singlet, no neighbors. Any questions? All right. Which of the following molecules will provide the following signals? Okay, so we want to look at our graphs here below and determine which molecule is represented here. Okay. So first of all, let's look at our IR graph and kind of pick out the important parts of it. Okay. So what does this 1600 represent? Anybody know? Perfect, C double bond C. If it was closer to 1700, you could think possibly a C double bond O, but right at 1600, you know that's gonna be C double bond C, perfect. Okay, what about 2200? You got a triple bond, okay? And it's either gonna be a C triple bond C or C triple bond N. Okay, and again, he's going to give you all of the keys for these. You'll know what the signals are. He'll give you like the graph that tells you, hey, you know, at 2200 you could expect to see triple bond C or C triple bond N. Okay, so don't stress too much about that. But our 2200 is going to be C triple bond C or N, and because none of our answers have C triple bond N, we can just assume it's a C triple bond C. Perfect. All right, our 2950 and our 3100, those are just our sp3 and sp2 CH bonds. And those are obvious because, you know, they're just below 3000 and just above 3000. Okay. And then what about 3300? Yep, perfect. SP. It can also be a benzene ring. Those are both within the both within that range. Okay, but because it's so strong, I would assume an SP bond. Okay, so you can't assume benzene ring, but it also, you know, all of these have a benzene ring. Okay, so we know we have a benzene ring probably. Well, all the answers have a benzene ring. Okay, we know that we have a C triple bond C and we have a C double bond C. Okay, now let's go look at our options and which ones we can cross out. Okay, so we know that B does not have a C triple bond C, so we can get rid of B. D also does not have a C triple bond C. Okay, so now we need to determine between A and C. So let's look at our HNMR graph and determine which one would have the correct hydrogens. Okay, so this 5H multiplet, do you guys know between 6.5 and 8, what does that represent? Okay, little trick here, anything between 6.5 and 8 on a HNMR graph, perfect 10er, is a benzene ring. Okay, any peaks between 6.5 and 8 is going to be your benzene ring. Okay, and when there's 5 hydrogens, you know it's mono-substituted. Okay, again, I'll say that between 6.5 and 8 is benzene ring. If it has 5 hydrogens, it's mono-substituted. Okay, because let's look at C, for example. Okay, you'd have 5 hydrogens around the benzene ring, right? Whereas on a di-substituted benzene ring, you'd only have 4 hydrogens. Okay. So we know that we have a mono-substituted benzene ring. So what do we think the answer is? Perfect, C. Okay, let's make sure that we also make sure that the rest of the HNMR lines up. So the 2 hydrogen singlet, that'll be this CH2 right here. Okay, those 2 hydrogens with 0 neighbors. And then this 1 hydrogen singlet will be the hydrogen on the end of the C triple bond C. Okay, so that's perfect. Everything lines up and that's our answer. Okay. How many degrees of unsaturation in the following molecules? Let's see, I wouldn't have picked C because I was told triple bonds don't bend. As far as the signal goes, Are you talking about these right here? Okay. I mean, C triple bond Cs do show up on H&MR graphs. So as far as like non-bending goes, that is true. But they do still show up on H&MR. So I'm not sure what you're confused on. Were you thinking they didn't show up?
No, I would have just ignored C because when they say that there's an SP rate, you see on C where the bend is, and then the triple bond goes up too.
Oh, I see what you're saying.
Yeah, I wouldn't have picked that one for that one reason. I would have just thought that.
It was an invalid structure.
Yeah.
Yeah, so some people draw it like that. Technically, it's more like A with a triple bond where it goes straight out. That is more correct as far as a drawing goes, but sometimes they do get drawn like that. So I wouldn't discount them. If you see a bend in it like that, you know, just kind of assume that it is going straight. I know it's kind of confusing. If you were drawing it, he would want you to draw it straight, but sometimes you find them online. Like this example was one I found on Google, and it was going up like that. But yeah, I'm sorry for the confusion there.
Oh no, don't worry. So if it was A, would there be a signal for the bromine somewhere?
Not on these two graphs. The only way you know there's a bromine for sure is on a mass spec, and you would see the signals from the mass spec where it's got the 1-to-1 ratio on the mass. You remember what I'm talking about with that?
Yeah.
So for this one, the only reason we knew it wasn't A was because we had a mono-substituted benzene ring.
Yeah, okay.
Okay, and A is di-substituted. So that's how we determine the difference there.
Oh, okay.
Yep. So no, we didn't know for sure if there was a bromine or not, but we could eliminate it because we knew the ring wasn't di-substituted. Okay. So let's look at how many degrees of unsaturation in these molecules. Okay. Do you guys know if he's going to give you this equation? I'm pretty sure he does. You guys remember him saying if he will or not? Yes, perfect. So all you really need to know is how to use it. Okay. So you're going to do 2 times the number of carbons you have plus 2 plus the number of nitrogens minus number of hydrogens minus number of halides, and then divide that whole thing by 2. Okay, so for this one, we have 4 carbons. So we have 2 times 4 is 8, plus 2, we're at 10. There's no nitrogens. We subtract the number of hydrogens, so we do 10 minus 8, okay, which is 2. Okay. Then we don't have any halides, so 2 divided by 2 is 1. Did everybody understand how I did that? I didn't really want to have to draw that out. But you just kind of go through the equation and do it that way. Okay, so for the second one, 2 times 10 is 20, plus 2 is 22. Okay, and then no nitrogens minus number of hydrogens is 14, so 22 minus 14 is 8. And then no halides, so then we do 8 divided by 2 is 4. So 4 degrees of unsaturation. Any questions on how I got those? All right, carrying on. So now we're going to want to draw the structure, okay, based just on the H&MR graph, and also having our chemical formula. All right, so I'm going to come out to the side over here so I have a bit more space to write. So I'm going to start with our integral values. Okay, so we have 11.9 divided by our lowest number, which is 6. We have We have 12.1 divided by 6. 6 divided by 6. We have 55 divided by 6. Okay. So 11.9 divided by 6 is about 2. 12.1 divided by 6 is about 2. 6 over 6 is 1. 55 over 6 is about 9. Okay. So now we look at this and we say, okay, so now we know we have 2 hydrogens in this peak. Let me just choose a different color. 2 hydrogens, 2 hydrogens, 1 hydrogen, and 9 hydrogens. Okay. What did I say about 9 hydrogen singlets? Can you remember? Tert-butyl, perfect. 9 hydrogen singlets are tert-butyls. How about peaks between 6.5 and 8? Benzene ring, right? And then we have 2 and 2 for our peaks here. So what does that mean for our benzene ring? Means it's di-substituted because we have 4 hydrogens, okay? You can kind of clump those 2 peaks together. The reason they're separate is because, depending on what the groups are, they're going to pull them a little bit differently, okay? But you know that, hey, there's going to be 4 total on our benzene ring, okay? So now we know we have a tert-butyl, we have a di-substituted benzene ring, and we have a 1 hydrogen proton somewhere as well. Okay, so let me see. They don't have a shape. All right, ink shape. Cool. So we have a benzene ring. Okay, and we need it to be di-substituted, and we know we have a tert-butyl, so let's just go ahead and draw a tert-butyl on one side. And we know we're going to have something else over here. It's di-substituted. Okay, so now let's look at our chemical formula and determine what we still need. So we have C10H14O. So right now we have 6, 7, 8, 9, 10, 11 carbons. Okay, so we have 1 too many carbons. And so we're going to have to replace this one with something. Let's go ahead and replace it with our oxygen. Okay. And then, so now we have the correct number of carbons. We have our oxygen. Let's count how many hydrogens we have. We have 9 on the end here. We have 4 in our ring. So we're at 13, and then we can add a hydrogen on the end of this oxygen, making it 14 hydrogens. C10H14O. Okay, now let's make sure that our H&MR graph is fulfilled. We have our tert-butyl group. Okay, we have 1 hydrogen singlet, which would be this hydrogen right here. Okay. And then we also have our 2 and 2 benzene ring. Okay, so that's how we find the structure. Any questions on that one? All right, let's carry on. So again, I'm going to come out to the side here to do our, I guess we don't need to do, okay, so they already gave us our integral values. 5 plus 1 plus 6 is 12, C9H12. Okay, so that's how many hydrogens are here. Okay. So let's look at these 2 peaks here. Okay, 1 hydrogen multiplet, 6 hydrogen doublet. Okay. What does that tell us? You guys remember what that tells us we have? Okay, this is going to be a isopropyl. Okay, because if you imagine an isopropyl group, we have 6 hydrogens, okay, with 1 neighbor, which is this hydrogen in the middle, and then we have 1 hydrogen with lots of neighbors. Okay, does that make sense? So when you see 1 hydrogen with lots of neighbors, 6 hydrogens with 1 neighbor, you know you have an isopropyl. Okay. And then what does this 5 down here between 6.5 and 8 represent? Yep, perfect. Is it a mono-substituted, di-substituted, tri-substituted? What do we think? Mono, perfect, mono-substituted. So let's draw our benzene ring. Okay. All right, we know it's mono-substituted, so it's just going to be something off on one side. Okay, and then we want it to have 9 carbons. So first we have 6, 7, 8, 9, because we wanted an isopropyl. Let's make sure we have the correct number of hydrogens. We have 5 on the ring, 6, 7, 8, 9, 10, 11, 12. So yes, we do have everything correct. Whoops. That is our structure. Any questions on that one? Okay. Let's do this next one. Okay. So we have 2 graphs here. We have an HNMR and an IR. Okay. All right. So we've got 1740. What does that tell us? C double bond O. Perfect. Okay. If it's more on the 1600 side, then it's going to be C double bond C, but closer to 1700 or above is going to be C double bond O. Okay. And then what about 2950? That's just our sp3CHs, right? Okay, so we know there's no C double bond Cs. We know there's no, any other craziness going on as far as IR is concerned. Okay, and then we have a 6 hydrogen singlet and a 4 hydrogen singlet. Okay, so this is kind of a tricky one. All right. So what do we think? What's going to happen here? There looks like there's a lot more hydrogens in all of these than just 4 and 6, right? Okay. I'm going to give you guys a hint. It is, let me think how I want to phrase this hint. This peak right here is quite de-shielded compared to most hydrogens, okay? So those are going to be near oxygens. Okay. So we know we need C double bond O, and we need to have 4 hydrogens near oxygens. Okay. So we know we need to have C double bond O so we can get rid of C. Okay. And we need 4 hydrogens to be near electronegative atoms. Okay. So here's our 4 hydrogens. Okay. Whereas here's our 4 hydrogens, and here's 4 hydrogens. Come on, there we go. Okay, which one do you think is going to be our 4 hydrogens that are more de-shielded? B, perfect. Okay, so that is our answer. All right, so a lot of people would get confused on this one and say, well, why can't it be D? Well, it's because it would be our 6 hydrogens on the ends here that would be more de-shielded because of these oxygens. Okay, so they would be flip-flopped. The 6 hydrogens would be more de-shielded. Okay, so you just got to watch out for that. It's a little bit finicky, a little bit tricky, but just be really careful. Make sure you're looking at which ones are more de-shielded and not. Okay, I'm going to go ahead and skip this problem. You guys can go ahead and look at the key for this one. The trick for this is to look for number or for any planes of symmetry. Okay, so I'll do this first one just so you know what I'm talking about. There's a plane of symmetry going down this way and also across this way. Okay, so you're only going to have 1, 2, 3 signals, okay, because everything else is matched on another part of the plane of symmetry. Okay? Again, there's going to be another plane of symmetry, so you're only going to have whatever ones you have on the top will be matched on the bottom. Okay, so look for symmetry, determine how many H&MR signals there will be. Okay, so here's some spectroscopy practice. I'm going to zoom out here a little bit. Okay, so we have a chemical formula, we have an IR spec, and an H&MR spec. Okay, so what's this 1716 going to be here? On the 1700s, it's going to be a C double bond O. Come on. Are you guys still there? Yeah, it looks like you're there. Okay, sorry. For some reason, my OneNote shut down. So let me pull this back up. Share screen. Sorry about that. All right, are you able to see my OneNote again?
Yeah, we can see it.
Perfect. All right, sorry about that. Okay, so this is going to be a C double bond O. All right, and then we have our sp3 CHs. Okay, so nothing too crazy there, but we do know we have a C double bond O. All right. Now let's look for patterns here in this H&MR. Okay. 2 hydrogen multiplet. Okay. And a 3 hydrogen triplet. When you see 2 hydrogens and 3 hydrogens next to each other, and the 3 hydrogen has a triplet, you know that it's going to be an ethyl group. Okay. So you know on the end of your molecule, you're going to have an ethyl group like that, because this is your 3 hydrogens with 2 neighbors, and this is your 2 hydrogens with potentially more neighbors over here. But if you see 3 hydrogens with 2 neighbors, and then next to it 2 hydrogens with at least 3 neighbors or more, then you know you're going to have an ethyl group. Okay, so that kind of helps you a little bit here. Okay. Then we know our chemical formula is C5H10O. So let's go ahead and just, as I like to do, I like to start with my, sorry, need some water, with my carbon chain, okay? And then we know we have a C double bond O, okay? I'm just gonna put that right here for now. Okay, I'm not sure where it goes yet, but I'm just gonna put it right there. Okay, and let's see if this fulfills our chemical formula first of all. So we have 5 hydrogens, or 5 carbons, 1 oxygen, and we have 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, okay? So our chemical formula is fulfilled. Let's make sure our graphs are all fulfilled. We have our C double bond O, and we have our sp3 CHs. We don't have any double bonds, C double bonds, C triple bonds, anything like that. Okay. Then we've got our ethyl group. We've got our group here. and our 2 hydrogens with lots of neighbors. Then we've got 3 hydrogens with no neighbors. That could be these hydrogens here. And we've got 2 hydrogens with 2 neighbors. That could be here. Okay, so that is our chemical structure. Okay, so again, just follow through the steps. Find out everything your graph tells you. See if there's any kind of hints like I talked about with the ethyl group. Draw a rough structure, see if it matches, and keep editing until you find the right one. Okay. This next graph, let's look at all the different things it tells us. What does this broad peak at 3300 tell us? OH, perfect. It's an alcohol, right? A broad peak at 3300 roughly is an alcohol group. Okay, we have our sp3 CHs here, and then everything else is footprint. Okay. Down here we have 1 hydrogen multiplet and a 6 hydrogen doublet. What does that tell us? Iso, perfect, isopropyl. Okay, so we know we have an isopropyl, and then we have a 2 hydrogen and then 1 hydrogen. If you look at the graph that Dr. Garg gives you to tell you what things are, this 1 hydrogen between 3.5 and 4, that's your alcoholic hydrogens. Okay, so that's on that key as well. So I'll just tell you that's your OH proton. Okay, because we know we have an alcohol. All right. So let's see if we can put together a structure. So we have C4H10O. Again, I just like to just start with my my carbon chain. We know we have an OH, okay, but we also know that there's an isopropyl. So let's take off one of these carbons and make an isopropyl. Okay, so we have our OH, we have our 4 carbons. Let's make sure we have the correct number of hydrogens. We're supposed to get 10. We have 3, 6, 7, 8, 9, 10. Perfect. So that fulfills our chemical formula. And let's see if our H&MR graph agrees. So we have an isopropyl, which is good. We have 2 hydrogens with 1 neighbor. Okay, these are our 2 hydrogens, and that would be its neighbor right there. Okay, so that matches up, and then we have our OH hydrogen. So that is our structure. Does anybody have questions on that one? Perfect. So I'm going to actually end our meeting there, and I will send you guys the key to the rest of this. I want you to try the rest of these on your own. And then if you have any questions at all, please feel free to message me through Canvas, and I'll be more than willing to help answer those for you. Is there any other questions before we finish up today?
No, I'm good. Thank you.
Perfect. Awesome. Thanks for coming, everybody. I'll send out this video as soon as it's ready as well.